Hello, good evening everyone. Just let me share the screen. Hello, good evening everyone. So welcome to the week 3 of this tutorial session for the course of Principles of Modern CDMA, MIMO and OFDM wireless communication system. So today we will solve questions based on the week 3 lectures which is uploaded on the NPTEL portal, and this video will be recorded and will be uploaded on YouTube for those who cannot watch it now. So today we will solve questions based on multiple antenna systems and bit error rate of multiple antenna systems. So before moving on to the tutorial part, we'll see little basics of it. We'll see the basics of multiple antenna system. We'll just wait for a minute. So we'll start the lecture now. Many students have joined. So let's assume like there is a transmitter at the base station. It is TX1 and there are two receivers as it is a multiple antenna system. So the first one is RX1 and second one is RX2. Here the symbol X is transmitted through the channel H1 and the received symbol is Y1, that is after adding the noise in the channel medium, and this is H2 vector and the received symbol is Y2. So at the receiver 1, the received symbol is H1X plus N1 and Y2 is equal to H2X plus N2. So the received vector Y bar will be the channel vector H into the symbol X plus the noise vector N. So we can write it as in the matrix form like this: H1, H2 x plus the noise vector, that is n1 and n2. The first one is the received vector. The second one is the channel vector, and the third one is the noise vector. Okay, and here what is our x? X is the transmitted symbol, y is the symbol received, n1 comma n2 is the Gaussian noise, and expectation of n1 comma n2 will be 0 because these noise are uncorrelated, so covariance will be 0. And the power of this noise is sigma squared. So now this we will take a y tilde, that is the multiplication of w bar t. This is a pre-coding vector, so that the SNR could be maximized at the receiver end. Now what is our w vector? W vector is w1 w2. This is known as pre-coding matrix. So y tilde, and this is multiplied with the received vector so that the SNR should be maximized. So this is equal to w bar t into h bar x plus n bar. So this we can write as w bar transpose h bar x plus w bar transpose n bar. So this is the signal component and this is the noise component. Okay, so what will be our SNR? SNR will be signal power by noise power. So signal power will be w bar transpose h bar mod square into power of the symbol x and expectation of this noise term, that is w bar t n bar. So this will become w bar transpose h bar mod square p by, this is uncorrelated, so this will be sigma square and norm of w bar. So now we have to find w bar transpose into h. So this will become w1 w2, and what is our h vector? That is the channel matrix h1 and h2. So this we can write as w1 h1 plus w2 h2, and this is equal to w bar h bar. So this we can write it as, so when it will be, this term will be maximum when cos theta is 1. So when is cos theta 1? At theta is equal to 0, this will become magnitude of w into magnitude of h bar. Okay, and this will become, at theta is equal to pi by 2, this term will become 0. Okay, so SNR is equal to P cos square theta by sigma square. So norm square of W will get cancelled. So this will become P by sigma square cos square theta. And at theta is equal to 0, the SNR will be maximum. Understood? So now, what is the SNR max value at theta is equal to 0? So that is P by sigma square magnitude of H square. Okay? And this we can write as P by sigma square mod of H1 square, because magnitude of H bar square will be mod of H1 square and mod of H2 square. So what is happening actually at theta is equal to 0? If theta is equal to 0, W bar and H bar will be in the same direction, okay? Are in same direction. So both the vectors align to each other. Both vectors align to each other. Okay, so this means W bar is directly proportional to H bar. So how we can write W bar? If it is in same direction, so it will be the vector in the direction of channel vector. So we can write it like this. So this is our W bar. And this pre-coding matrix W bar is known as maximal ratio combiner, MRC, which is taught in this lecture, and we'll solve some questions based on this as well. Up to this, I hope it is clear. So now let's take a question. Example, let's have one example. Like at the transmitter end at the base station, there is one transmitter antenna TX1, and at the user terminal there is two receiver RX1 and RX2. Okay, and this is the channel vector H1 and H2. And in this question, H1 is given as 1 by root 2 plus 1 by root 2 j. H2 is given as 1 by root 2 minus 1 by root 2j. And the noise power sigma 1 squared, sigma 2 squared is given as half. So we have to find the SNR. So in this case, what is the received vector as we have studied in the beginning today? H bar x plus n bar. So we can write it as y1, y2. This is the y vector, and h vector is 1 by root 2 plus 1 by root 2j. 1 by root 2 minus 1 by square root 2j. Again x plus the noise power, that is half and half. So for maximizing SNR, the optimal MRC vector, maximal ratio combiner vector, W bar is H bar divided by magnitude of H bar. Okay, it is in the direction of channel vector. So here magnitude of vector H is given as mod of H1 square mod of H2 square, that is under a square root. So here we can write it as, what is the magnitude of H1? That is square root of 1 by 2 plus 1 by 2. Again this is the square of it because it's mod of H1 square. Again half plus half square. So this will become 1 plus 1. So this is equal to a square root of 2. So what is the precoding vector? W bar, that is H bar divided by norm of H. So this is 1 by root 2. What is our H bar? That is 1 by root 2 plus 1 by root 2j, and it is given here 1 by square root 2 by minus 1 by square root 2 of j. So when we multiply it, we'll get as 1 by 2, or let it be in this, we will multiply it later. So what is now SNR? As we have studied, SNR is equal to, as this term is complex, we will take Hermitian instead of transpose. Okay. So what is W bar Hermitian? That is W transpose conjugate. So now here W bar Hermitian H bar. This is given as, what is our W bar? W bar we have found it here. So what is this? 1 by root 2. So this is our W bar. It's Hermitian. So we have to take transpose of it and then conjugate of it. And then we have to multiply with H bar. So let's do that. So this will become, transpose will become minus 1 by root 2. Sorry, transpose and conjugate we will take together. So here this sign will become minus. And the second term will become 1 by root 2 plus 1 by root 2j. And our H vector. So this is our H vector. This complete is our W vector. So let's write the value of H vector. So after this multiplication, we will get this term will be first term. So it will become 1 by 2 minus 1 by 2, and this j square, it will become again plus 1 by 2 and minus 1 by root 2 j square. So again this will become 1 by 2. Understood how it came? So now this will become 1 by root 2 into 2. So this will become root 2. So our W bar Hermitian H bar is root 2. So SNR is equal to root 2 square power by sigma square. And sigma square, how much it is given? That is half. With 2p by half, it is equal to 4 times the symbol power. Okay? So SNR MRC. This is SNR MRC. So this is equal to 4 times the symbol power. So now we'll solve some questions based on the lecture series, and we'll use directly the formula and we will see the question. As all the formulas are derived in the classroom, so we will not go for the derivation. We'll directly see the formula and directly solve the question. The diversity order D of the additive Gaussian noise channel Yk is equal to Xk plus Nk is given as. So here the diversity order D, the formula is D is equal to minus limit SNR tends to infinite log half e to the power of minus half SNR. Okay, divided by log of SNR. Okay, so now D will become minus limit SNR tends to infinite and so this actually the diversity order is the formula I will write, and this is for the AWGN channel. Okay, so actually it is log SNR and it is the probability of error in AWGN channel divided by the log of SNR. So this term we know this is derived in the first lecture, so that's why we directly put that value there. So now our D will become minus limit SNR tends to infinite. From here this came, and it will become log of half plus minus half of SNR. Okay, divided by log of SNR. So this will become as log of half is very less as compared to SNR. So this we can make it negligible. Okay, so this will become, and this minus and minus will get cancelled. So this will become limit SNR tends to infinite half of SNR divided by log of SNR. And we know here it is, this is the limit of the form infinite by infinite. So we will use L hospital rule. So D is equal to limit SNR tends to infinite, and we'll take the derivative of numerator and derivative of denominator. So it will be half and 1 by SNR. So this will become SNR by 2, and limit SNR tends to infinite. So the diversity order will become infinite. So for this question, option B is the correct answer. Now we'll move on to the second question. The approximate bit error rate for high SNR in a system with L is equal to 4 antenna and independently fading receive L equal to 4 independently fading receive antenna is. So we know that as derived in the classroom for high SNR, the bit error rate is given as 2L minus 1 choose L into 1 by 2 SNR to the power of L. So this equation is very important, and this is approximate bit error rate for multiple antenna system. Okay, so now our bit error rate is given as L is equal to 4, and how this formula came, that also we will see, but first we will solve this question. So it will be 2L minus 1, that is 8 minus 1, 7C4 1 by 2 into SNR to the power of 4. So it will become 7 factorial by 4 factorial by 3 factorial into 1 by 16 SNR to the power of 4. That will become 5 into 6 into 7, then 6 and 6 will cancel. It will be 35 by 16 SNR to the power of 4. So option B is the correct answer. And one more thing. When SNR is not given high, in that case, bit error rate will be 1 minus lambda by 2 to the power of L summation L is equal to 0 to capital L minus 1 L plus L minus 1 CL 1 plus lambda by 2 to the power of L. Okay, and lambda is equal to square root of SNR by 2 plus SNR. So I will give the reverse arrow because this is a generic formula, but this is for high SNR. Okay, and this is our general bit error rate for multiple antenna system. So now let's take one example. Before that, let me check this video is getting recorded or not. Yes, it is getting recorded. And also this will be uploaded on YouTube and the link will be provided to you. We'll take one example using the assumption of high SNR approximation find bit error rate for multi-antenna system where L is equal to 2 antennas for SNR in dB value is equal to 20 dB. Okay. So SNR is given as 20 dB. So let's convert it into normal terms. So that is 10 log to the base 10 SNR is given as 20. So this means when SNR is given in dB. So now our SNR will be 10 to the power of 2. Okay. So this is 100. Now approximate bit error rate for high SNR value. What we have seen here, we have seen the formula. Same formula we will use. That is equal to 2L minus 1 CL 1 by 2 SNR to the power of L. So this will become, here L is equal to 2 antennas. It is given in the question. It will become 4 minus 1, 3 C2 1 by 2 SNR to the power of 2. It will become 3 by 4 into SNR square. That is 100 into 100. So the final answer will be 0.75 into 10 to the power of minus 4. Or we can write it as 7.5 into 10 to the power of minus 5. So this is the bit error rate for L is equal to 2 antennas when SNR is given as 20 dB. Okay, so now we will move on to the next question. If you have any doubt, you can ask. Coming to the next question, that is given as, consider an L is equal to 3 receive antenna wireless system. So here L is equal to 3 receive antenna. So this means there are 3 receiver at the user terminal. And the noise variance is given as minus 3 dB on each antenna. It is not the total, it is on each antenna. And considering the weighting vector with combination weights, W1 is given as 1 by root 2 plus J 1 by root 2. W2 is given as 1 by root 2 minus J 1 by root 2. And W3 is given as square root of 2 plus J into a square root of 2. So now, what is the approximate dB noise variance at the output of the maximal ratio combined? So, what we will do? First, we will find the magnitude of, we have to find actually what is the approximate dB noise variance. So, for the maximal ratio combiner, what we have seen, it is sigma squared and magnitude of W square. So here you can see for noise, this is the term. Noise power in MRC is given as sigma square into norm of W vector square. So we have to find this value. So first let's see. So this is equal to square of the magnitude of W1 square plus W2 square plus W3 square. So now W1 is mod squared will be square root of 1 by root 2 square plus 1 by root 2 square the whole square. Okay. Again, same it will be for this also. For W3, it will be square root of root 2 square plus root 2 square the whole square. So this is given as half plus half, it will be 1. So 1 square will be 1 plus 1, and this will be 2 plus 2, 4. And the square root of 4 square will be 4. So this value is 6. And sigma square is given as in dB as minus 3 dB. So we can write as 10 log 10. Sigma square is minus 3. So sigma square will become log 10 sigma square will become minus 0.3. This implies that sigma square will become 10 to the power of minus 0.3. So this is 1 by 2. So what is the value of sigma square? Norm of W square, that is half into 6 into, it will be half into 6 because sigma square is half. So this is equal to 3. So noise power is 3. Now in dB, how we will find? We will find 10 log 10, 3. So that is equal to 10 into, and log 3 to the base 10 is 0.477 dB. So this will become 4.77 dB. If you have any doubt, you can ask. We'll move on to the next question. Question number 4. Consider a multiple receive antenna wireless channel with 12 antennas. Okay, 12 antennas at receiver. And h of I is given as h of 2L minus I plus 1 for I is in the value from 1 to L. And HI is the IID Rayleigh fading channel coefficient. So diversity order of the system is. So the diversity order D is given as minus limit SNR tends to infinite divided by log of SNR. So here for L antenna, probability of error is given as 2L minus 1 CL 1 by 2 SNR to the power of L. Now for 2L antenna, it will be given as 2 into L. So L is here 2L. So it will become 4L minus 1 C 2L 1 by 2 SNR to the power of 2L. Okay. The diversity order D is equal to minus limit SNR tends to infinite and probability of error is given for 2L antenna is log 4L minus 1 CL, sorry, C2L 1 by 2 of SNR to the power of 2L. Okay, divided by log of SNR. So now D will become minus limit SNR tends to infinite log 4L minus 1 C2L plus log 1 by 2 SNR to the power of 2L divided by log of SNR. This D will become minus limit SNR tends to infinite log of 4L minus 1 C2L. Now this will become minus 2L log 1, so it will become 0, and minus 2L log 2 of SNR. So now this term, here SNR is tending to infinite. So now divide it into two terms. Log 4L minus 1 C2L divided by log SNR minus 2L log SNR divided by log SNR. So sorry, here it is 2 SNR. So again we can break it into two different terms. So we can write it as 2L log 2 by log SNR and again minus 2L log SNR divided by log of SNR. Okay, because this is 2 into SNR. So it will become, this term will become log 2 plus log SNR. Same thing we have done. So now here you can see SNR tends to infinite. So something finite quantity by infinite quantity will become 0. And this will get cancelled. So here D is equal to minus limit SNR tends to infinite. This whole term will tends to 0, 0, in 0 minus 0 minus 2L. So finally diversity is equal to 2L. This minus and minus will get cancelled. So diversity will be 2L. Option B is the correct answer for this question. So move on to the next question if you don't have any doubt. Coming to the next question. Consider a wireless channel with two receive antennas and single transmit antenna. Given that Rayleigh fading wireless channel coefficient for both the links are independently fading with average gain 1 by root 2. So first of all, there is one transmit antenna TX1 and there is two receive antenna RX1 and RX2. An expectation of channel vector is 1 by root 2. So HI is the fading channel coefficient for link I. The bit error rate as a function of SNR is equal to P by sigma square, where P is the transmit power and sigma square is the noise power, is given as. We have to find the bit error rate. So here SNR is given as P by sigma square. We have to find bit error rate in terms of SNR. Okay. And also it is given the Rayleigh fading wireless channel coefficient, both the links are independently fading. So the gain factor is 1 by root 2. Okay. So SNR will be 1 by root 2 of SNR. Because the actual SNR is faded with the gain of 1 by root 2. So now again, bit error rate is 2L minus 1 CL 1 by 2 SNR to the power of L. So this is the very important formula. So here put L is equal to 2. L is equal to 2. So we will get 3C2 1 by 2 and SNR E is how much? 1 by root 2 SNR and to the power of 2. So it will become 3 into 1 by root 2 SNR square. So this is equal to 3 by 2 into SNR square. So option C is the correct answer for this question. We move on to the next question. Question number 6. So just a 1 minute break we'll have now. So okay, moving on to the next question. Consider a wireless system with L is equal to 4 antennas and channel coefficient H1 is given as 2 plus J, H2 is given as minus 1 plus 2J, H3 is given as minus 2 minus J, and H4 is given as 1 minus 2J. So let the noise variance sigma square is equal to half. Okay, and transmit power P is equal to 3 dB. So the SNR at the output of the MRC is approximately. So they are asking the SNR of MRC. And SNR of MRC is given as mod of H squared P by sigma squared. Because there was a term W bar squared in numerator and denominator. So this is cancelled because this is asking MRC. So theta is 0. So in SNR MRC, cos squared theta is equal to 1 as theta is equal to 0. This we have already studied. So now the norm of H squared is given as 2 squared plus, so we can write this as mod of H1 squared plus mod of H2 squared plus mod of H3 squared into P by sigma squared. So this we can write it as from the given value of H 2 squared plus J squared plus minus 1 squared plus 2J squared plus minus 2 squared plus minus J squared plus 1 squared plus minus 2J squared. Sorry, j term we will not take here. We will take only one. 1 square, 2 square, minus 1 square, and this will become minus 2 square. So finally we will get this whole multiplied with power by sigma square. So we will get 4 plus 1 plus 1 plus 4 plus 4 plus 1 plus 1 plus 4 into power, and sigma square is given as half. And power is given 3 dB. So 10 log 10 p is equal to 3. So p is equal to 10 to the power of 0.3. So this value is 2. Okay, because 10 to the power of minus 0.3 is 1 by 2, as we have seen just now. So this is equal to 10, 14, 15, 16, 20. 20 into 2 by half. So this is 80. So SNR using maximal ratio combiner is 80. So SNR MRC in dB is equal to 10 log 10 to the base 80. So this is equal to 10, and log 80 to the base 10 is 1.9. So this is equal to 19 dB. So is there any answer? 19 dB? Yes, option C is the correct answer for this question. We'll move on to the next question. The gain G of the maximal ratio combiner is given as mod of h squared, where h is the channel vector in multiple receive antenna wireless system with independent identically distributed IID Rayleigh fading coefficient for L is equal to 4 antennas. So the function, like the distribution function of FGG, is given as z to the power of L minus 1 divided by L minus 1 factorial e to the power of minus g. So here L is equal to 4. So this will become g to the power of 3 divided by 3 factorial e to the power of minus g. So it becomes 1 by 6 g cube e to the power of minus g. So the distribution of gain is given by 1 by 6 g cube e to the power of minus g. Option D is the correct answer for this question. Move to the question number 8. So if the bit error rate of communication system decreases as 1 by SNR cube plus 1 by SNR to the power of 4, the diversity order of the system is. So bit error rate is proportional to 1 by SNR cube plus 1 by SNR to the power of 4. As we know, signal to the noise ratio to the power 4 is much greater than signal to the noise ratio power 3. So this term will vanish for high SNR. Okay. For high SNR, we will have bit error rate is directly proportional to 1 by SNR to the power of 3 only. Okay. So the diversity order of the system is 3. So diversity order of the system means like the power of SNR by which the bit error rate will decrease. So it is 3. Option A is the correct answer. Why we have written like this? Because if this is given, then 1 by SNR cube is much greater than 1 by SNR to the power of 4. Okay, and this is our dominating term. So option A is the correct answer for that question. Now in this question, there is a L antenna wireless fading channel. HI is the fading channel coefficient. YI is the received symbol on antenna I, and pi I denote the phase of HI. The output of the equal gain combiner is. So the output of the equal gain combiner will be, just give me a second. So this will be given as e to the power of minus j pi I into y. Okay. So this is our y tilde, and summation will be from I is equal to 1 to L. So option B is the correct answer for this question. Now moving to the question number 10. What is the approximate SNR required to, where do we get similar problem? Might be in the book. You can check the book of Professor Aditya Jagannathan. So in there is lots of practice problem at the end of the exercise. You are not audible.
Yeah, my audible, sir.
Yes, yes.
Yeah, any other book, sir? Any other book if it is not available right now?
You can,
Any other book for similar kind of problems for more practice?
as I have seen, like the book of Aditya Jagannathan sir is having similar question, but I don't know which other book will be having the same.
Sir, Aditya Jagannathan sir book, whether any soft copy available or hard copy, how to get, sir? Whether soft copy available?
You can
Even
check on the internet. It is available, I guess. You can check.
Amazon पे available है soft copy और hard copy.
In Amazon, it is available both hard copy and even on the internet you might get.
Okay, sir, I will check. Same title. What is the title, sir? Same. Why the CDMA?
Let me check
I
once.
I know why the CDMA same title.
Just a minute. Let me check. It is available on Amazon. It is the book title is Principles of Modern Wireless Communication System Theory and Practice.
Okay, sir. Okay.
There are lots of practice problem on that, so that also you can check.
Okay, sir.
Coming to the 10th question, that is what is the approximate SNR required to achieve bit error rate, that is 3 by 4 into 10 to the power of minus 12 wireless system with L is equal to 2 receive antenna, and it is given as it is a maximum ratio combining. So in this, the bit error rate is given as 3 by 4 into 10 to the power of minus 12, and L is equal to 2 antenna is given. But we know the formula for bit error rate is 2L minus 1 CL 1 by 2 SNR to the power of L. So here when we do, like when you substitute the value and equate it and put L is equal to 2, so we will get 3C2 1 by 2 SNR to the power of 2, that is equal to 3 by 4 into 10 to the power of minus 12. So again it will be this 3 by 4, 1 by SNR squared. So SNR square is equal to 10 to the power of 12. So this is imply that our SNR is equal to 10 to the power of 6. Now for making it into dB is equal to 10 log 10 this much dB. So this will become 60 and log 10 to the base 10 is 1. So this will become 60 dB. So for this question, option C is the correct answer. So today we will stop the lecture here only, and again we will meet on the next Tuesday. Yes.
Assignment to some seven questions that I have doubting the questions. Can you
Assignment
please?
2 deadline is over.
It is
Okay, so you can ask in the forum there also. Like I don't have right, like I have not enrolled in this course, so I don't have the assignment question. So you can ask on the forum, so there the TA will reply. Thank you so much. So we will end the lecture here only. We'll meet again next Tuesday at the same time. And after that we'll meet on Saturday from week 5.